This script is the demonstration of the learning objective 1 to draw the inference line diagram of the reaction of the shear force and of the bending moment. Okay, that is the learning objective 1. And then we will put the given uniformly distributed dead load. If you have it, it's going to be dl, the dead load, and uniformly distributed of 150 kilonewton per meter. And the concentrated live load, that is going to be LLF of 50 kilonewton. We will put these two loading into the inference line diagram to determine the maximum reaction and to determine the maximum moment. That is going to be the learning objective 2. Okay, so let us practice first by draw the inference line diagram. We will use the Mueller-Best law principle to draw the inference line diagram. First, they ask us to draw the inference line diagram of the support D. So you may recall from the Mueller-Best law, if we like to draw the inference line of reaction at C, so we got to eliminate the resistance of C sub y out. Okay, just eliminate it. And then you put the C sub y into that position to move this point into 1.0 unit. Okay, so before you can move, you got to fix this one with the fixed support. This is fixed support. Okay, and then we have hinge here, and this portion link, okay, in the form what we so call the rigid beam. When this all are rigid beam, portion of the beams are rigid beam, so the change in the shape of the beam will be in linear manner. Okay, and then since this one is fixed, okay, and this one is the hinge, and then you put the C sub y in that direction. The hinge here gonna be the rotating point, and then the shape of the beam will move like this. Okay, and if you scale it by a half centimeter to be 1.0 unit, and then the shape of the graph will be like this. And what is the coordinate of this? As you may know, if this is y, we will have y divided by 2, 4, 6, 8. Y divided by 8 equal to what? Equal to 1 divided by 2, 4. 1 divided by 4. So you got y equal to 8 over 4. That is going to be 2. That is the Mueller-Best law principle. If you like to draw the inference line of reaction, you eliminate the resistance or you eliminate the support, okay, of that reaction, and then you put the reaction to move the beam segment for 1 unit. The obtained shape is the inference line diagram of the reaction. Next, let us consider the inference line diagram of shear force at D. Okay, before we can do that, at D is here. The support here is fixed. Just put it fixed. And this is hinge, and this is roller. The support are the same. And if you like to draw the inference line diagram of shear force as D, the Mueller-Best law said we going to eliminate the shear force at point D. By eliminate the shear force is the relative displacement. We put the roller guide into that point D. Okay, and when you put the roller guide then you may again like before you put the V sub D, okay, V sub D to move the beam, and the shape of the beam will be the inference line of the shear force SD. And also we should to recall that if we cut a section of a beam, okay, this is very long beam, for example, you get what? You get the moment gonna be like this to be positive M. And also by doing that, the shear force on the left is gonna be downward, on the right is gonna be upward. So this is gonna be the sign convention of positive V and positive N. And then what happened? This portion is fixed, okay, to the wall. And then if you put the V sub D down here, what happened? There is no movement of this portion because it's very steep, okay, it's very steep. And then if this one won't move, the thing is this one gonna move for 1.0 unit, okay, that's it, obligation to draw the shear force inference line of the shear force. And also what happened is the portion of this must in parallel with this rigid beam, okay, and that will make this hinge move also. And then the last one, this one, when hinge move, this is the rigid beam have the rotating point at C, so this one gonna move like this, okay, and then you get the rotating BECF to be the shape like this. And what happened is this is gonna be 1.0 and this is gonna be Y, okay, and you're gonna have Y over what? 2, 4, yeah, Y over 4, right? Y over 4 equal to 1 divided by 2, 4, 1 divided by 4. So you will have Y equal to 4 over 4 equal to 1, okay, and since this is negative, okay, so this one is going to be minus 1.0. That is the inference line for the shear force at D, okay. Next, they still ask us to draw another inference line of shear force, but this time they said at E, okay, as E. Where is E? E is here, okay. Before we interested in that, we put this one as a fixed support as before, and this is hinge, this is gonna be the roller. And to draw the inference line diagram at point E, we do what? We eliminate the resistance of shear force at E. By eliminate that the shear force at that point, we put the roller guide into it, okay. And then we like to move this one, we put the what? Plus V sub D to act, okay, along the guideline, okay, roller guide. And again the same thing happened. This portion won't move because it fixed support won't rotate, so it won't move, okay. And by the rotating here, this one have the hinge and this one move downward, okay, and it's going to move downward forward, is going to move downward by minus A over L, okay, that's A over L, and it's going to move upward plus B over L. And what is A? You go back to consider this, okay, and your interesting span is here, so the L will be 4 meter, and this one gonna be the A, this one gonna be the B, so we get this one minus of what? 2 divided by 4. or you have minus 0.5. Same thing is over there. It's going to be plus 0.5 movement. Okay, and then you have this is half. When this is half, so this is going to be 2.5 millimeter. And then you get this portion to rotate like this. And this portion also 2.5. And then you get this rotation. And the sum of this gonna be what? The sum of this gonna be 1.0. Okay. And one more thing, they are gonna be in parallel. Okay. And also, if this is y, you will have this is for y 2, 4, y divided by 4 equal to this is 0.5, right? It's going to be 0.5 divided by 2 So you get y equal to 0.5 times 4 and divided by 2. So it's going to be 2 divided by 2 is 1. However, it's in negative. So this one is minus 1.0. Okay, that is another inference line diagram of shear force at E. Okay, and next we're going to draw the inference line diagram of the bending at point D. We go back to the point D. Point D is here. What we do is eliminating the resistance to moment at D. So we're gonna put what? We're gonna put the hinge into at point D. Okay, and this hinge going to be the same. The support here going to be the same. Okay, this beam is rigid connect will be the same, and the one more thing, the roller SC is here. Just put it here, and then what should you do? Just put the moment M sub D. This is D positive M sub D positive M sub D to X here. And then what happened is, this is stiff beam, and then if you like to rotate it, the fixed support won't allow the rotation, see? So this one will not move at all. So what happened is the portion here must move, and it must move for 1.0 radian. Okay, and then since this is 2, okay, and this is rotated by 1.0 radian, so this one gonna move to here, and this is gonna be minus 2, and then you get the shape of this to be like this. And again, this is rotating point. When you move this one like this one gonna rotate in this shape, right? Okay, we have what? We have this connecting point. All the beam segment must rotate in the straight line because they are rigid beam. Okay, and then if this one is minus 2 divided by 4, this one gonna be y divided by 4. So we can calculate this to be plus 2.0. Okay, next, the last one, we gonna consider what the point E. Now we going to the inference line of E. E is where? E is here, as we know. Okay, as we know, E is here. So we must eliminate the resistance to bending moment at E. That means again we put this hinge into E, and this hinge still the same. The support here fixed, and we also have the roller here. And what happened is, we got to put the M sub E, the positive M sub E as before, as M sub D here, positive. This one and this one is going to be positive M sub E. what happened is this portion again won't move, but this time we have what? We have the hinge here, and now we trying to open it up. Okay, so when you open it up like this, you may see the link between the tips of the pens, right? So this one gonna move to somewhere here with what? With the coordinate of A, B divided by L. It's going to be 2 times 2 divided by 4, which is 1, right? Which one? So this one gonna move by our scale to here. Okay, only this. And this is going to be 1.0 plus. And this one gonna move up to link this, right? And this one gonna move downward like this, and we have, oh sorry, this is more than we need. Okay, y, and then y divided by 2 plus 2, 4 equal to, this one is 1 divided by 2, so we have y equal to 4 divided by 2, and then it's gonna be 2.0. And since it's in lower area, so it's going to be minus 2.0. This is the first objective of our learning, to draw the inference line diagram, okay, of the given beam. And next, the learning objective 2, we will find the loading pattern. Again, please recall that we have what? We have the distributed, uniformly distributed dead load. The dead load have some characteristic. One is going to be distributed along the whole length of the beam, because most of the dead load is the cell weight of the beam. You cannot eliminate it. It's going to be total there. And another one, we have the concentrated life load. Okay, that is going to be a kind of point load. When you point it, you're going to find the maximum coordinate for the most influence area, or it's a larger area. Okay, let's ask first, they ask us to find the maximum reaction at support C. That means we're going to use this inference line as support C. And then they ask us to the maximum at moment at E. So we're going to use the inference line of the bending moment as E, right? Okay, let's remove this one a little bit like this. And then here we come. Okay, we have the beam there. Here, inference line of R sub C is here. And if we like to find the loading pattern, we can see that the area of the inference line of C sub Y, all of them are plus. Okay, so the concentrated life load gonna be at largest coordinate. So we will put this concentrated life load of 50 kilonewton at this point. So for that reason, you will get the concentrated life load here. Okay, 50 kilonewton. And for the dead load, it's going to be along the length of the beam. Okay, unlike the concentrated life load. If we have the concentrated life load for this problem also, we will put the concentrated life load in this area. Okay, or you may put it like this on the top of the dead load. Okay, but this one we won't have, just take it out. So this loading pattern gonna produce the maximum C sub y. And then recall back the point load gonna time what? Gonna time the coordinate. Okay, the coordinate here is 2, so it's gonna time 2.0. Okay, and the uniformly distributed load, sorry, is 150 kilonewton meter. Gonna time what? Gonna time the whole area of this inference line diagram. So it's gonna plus 150 kilonewton per meter, and the whole area is what? It's gonna be 1/2 of what? Of the base. 2468 times 8, and then time over here is 2. Okay, so what we have here is, over here is gonna be 100 kilonewton. This is 100 kilonewton, 50 times 2, and it's going to plus, this is cut 8 times 150 is going to be 1200 kilonewton. So finally we get the C sub y by this loading pattern to be the maximum as 1300 kilonewton. Okay, that is understandable, right? And the second one, now we come to find the loading pattern for the maximum moment at E. Let me zoom this because the moment E is here. So what we have is, there is two areas here. When we determine the maximum influence, we will consider the area under the influence line diagram. If the area is larger, is going to produce the larger influence. It's going to be the governing portion. Okay. Anyway, the distributed dead load won't make anything. Just put the 120 kilonewton per 150 kilonewton per meter as before along the whole length. Okay, and then we can consider the influence of this. This is going to be 1/2 of what? Of 4 meter, and then time this one for 1. So this one gonna be 2. Okay, the area is 2. This one is 1/2 time 2 plus 2 time 4 and time 2. So this one gonna be 4. So the negative area, the yellow area, gonna produce maximum influence for M sub E. Okay, so what we should do is we're going to put this 50 kilonewton, okay, at the largest coordinate of this yellow area. So if that happens, you got the same loading pattern, okay, and the M sub E gonna be 50 kilonewton, and time what? Time this one time minus 2.0 is negative. Okay, and some of the area here gonna produce the negative also, right? So it's gonna be plus 150 kilonewton per meter, and time this area, and this area is 4 negative, so time minus 4, and the other portion here gonna produce positive effects. So you pass this one for 150 kilonewton meter, and then you get what? You get this one for minus, so plus 2, sorry, plus 2. So we will have this one for minus 100. This one is minus 100. This one could be minus 600. minus 600. And this one gonna be plus 300. Okay, and finally you get the m sub e of minus 400 kilonewton meter. See, that is quite understandable, right? You guys will do it with some listening. Okay, it's not a guess. You must do it with something that's explainable. And then you got this for 1300 kilonewton. And the moment at E of minus 400 kilonewton meter. Okay, this is the end of this example, and I hope you guys trying to understand it and work on this example by yourself with hand calculation. Okay.